Okay, guys, last few topics and then we're all set with chapter 9. Right now we're going to do the bond energy information, and then I'll wind up by talking to you guys about bond length and bond order. But let's first focus on calculating the delta H of a reaction using bond energy information or bond energy data. You get this bond energy data from the table in your book. You do not have to memorize these numbers. It will be given to you, and OWL will have them also. So this is the table. This is what it looks like. It's table 9.5. And the calculation is to get delta H of a reaction. Remember, we did delta H of a reaction using calorimetry, using Hess's law. Well, here we do delta H of a reaction if you know this, if you add up the bond energies of all the reactants and then subtract the sum of the bond energies of all the products, you'll get the delta H of a reaction. It's more of an approximation, but it works. What I do is rather than add up every single bond energy of every single bond in all the reactants, I just focus on the bonds that I'm going to be breaking or forming, okay? So let's take a look at this reaction over here. Methane plus chlorine will give you methyl chloride plus hydrochloric acid. This is a typical organic chemistry reaction. It's a halogenation of an alkane reaction. Those of you who at some point will take 1060 or move on to organic 2260 will become very familiar with this reaction. Anyway, so this is a reaction and we want to know delta H of that reaction. The best way to do this is to draw out Lewis structures so that you can actually see which bonds are going to break and which bonds are going to form. So this is methane. So we've got these Lewis structures going. Oops, put a hydrogen here. This is methyl chloride or chloromethane and hydrochloric acid. Okay, so you can see, I'll do it in blue. I thought I had red somewhere. That's okay, I'll do it in blue. So you can see what's going on here. You are going to be breaking one carbon-hydrogen bond, okay? So we're going to break a carbon-hydrogen bond. We don't have to worry about these guys because we're not touching them. And we're breaking a chlorine-chlorine bond. Okay, so those are the things, these are the reactants, these are the things that we're going to change in the reactant side. And then what new things are we forming in the product side? We're forming a carbon-chlorine bond, and we're forming a hydrogen-chlorine bond. So you need to look up those numbers. You need to look up the bond energy of carbon-hydrogen and bond energy of chlorine-chlorine. So look them up. Carbon-hydrogen, I have it over here, but let me double check in this book. Carbon-hydrogen. Says here 413. Okay, so this is 413 kilojoules per mole. Chlorine. Now your OWL might give you different numbers, so don't worry about that. Just use whatever OWL gives you. And on an exam, sorry, hopefully you can hear me. On an exam, I'll be giving you these numbers, okay? So chlorine is 242. 242 kilojoules per mole. Now we want a carbon-chlorine. Again, I'm just looking at this table, guys. That's what I'm looking at. I want a carbon-chlorine. So carbon-chlorine chlorine. Carbon chlorine is 328. And then hydrogen chlorine is 431. So how do we do this? We add these two guys, 413 plus 242 minus 328 plus 431. Okay, so get your calculator, plug everything in. Let's see what we get. 413, oops, helps if I plug it in right. 413 plus 242 minus, open parentheses, 328 plus 431, close parentheses, and I get negative 104 kilojoules, equal to negative 104 kilojoules. So you can tell from this that this reaction here is exothermic, and you are going to be producing 104 kilojoules of energy will go out to the environment or to the system. Okay, good. So that's how you do it. Let's do another one. Okay? All right, here's another one. You get the idea. I like these. You will definitely have something like this on an exam. I'll be giving you all the bond energy data. You just have to decide what's being broken, what's being formed. If you don't want to do that, then you're going to have to account for every single bond, add all the reactants, all the bonds of the reactants, minus all the bond energies of the products, and you should get the same answer. But it kind of wastes your time to do too much like that. Just focus on the things that are being broken and formed. All right, here we go. Here's another one. I'm just going to go ahead and do the full structure here. This is something called ethene. And this is a halogenation of an alkene. So the double bond is going to break, and both chlorines are hooking up. Going to end up with a dichloroethane. Again, I love organic chemistry. Hopefully one day you will take it and enjoy it as much as I did. I teach the 1060, but I don't teach the 2260. All right, so here we go. So what are we doing here? We are going to be breaking the double bond. Okay? So you're breaking a carbon-carbon double bond. That's your breaking. And you're breaking a chlorine-chlorine single bond. Okay? What are you forming over here? You're forming a carbon-carbon single bond, and then you're forming two carbon-chlorine single bonds. Okay? So we look up the numbers. Carbon-carbon double bond is, according to this, it's 614. So 614 kilojoules. This is 614. Chlorine, we look that up. Chlorine, oh, that we did that one already. 242. So you're adding up this and this, because those are the things you broke on this side. I don't care about any of the carbon hydrogens. I didn't do anything to these guys. Okay, so I'm not going to include them. All right, and then you're forming a carbon-carbon single bond. So you look up carbon-carbon single bond, and that's 348. And then you have two carbon-chlorine bonds. So we go to the carbon-chlorine, that's 328, but we want two of them. So two, what did I just say it was? 2 328s. 2 328s. Okay, there it is. So let's plug it into our calculator. Again, these are the reactants, these are the products. So 614 plus 242, and then we're going to go minus 348, minus, and then open parentheses, 2 times 328, close parentheses. I have minus 148. I hope I did this right. I have different numbers here. I don't know why. Shouldn't be that much of a difference. Oh, the double bond in this book is different than the double bond in another book. That's okay. This is something to be expected. You'll see different books have different values. I guess these are all approximations, so don't worry about it. Minus 148 kilojoules. So basically, this reaction also is exothermic, and this is how much energy is going to be released. All right, on an exam, you will be given a list of bond energy values, and you just use those. And again, really straightforward. You shouldn't have any difficulty doing this. All right, last thing we're going to do in this chapter is I just want to talk to you guys about bond length. What is bond length? That is basically the distance between the nuclei of two adjacent atoms in a molecule. And so let's say you have a carbon and a chlorine. Here's a carbon atom and a chlorine atom. So here's a carbon, and then here's, let's say, a chlorine, and here's this and this. And all you do is that you measure this radius, and you add them together. So you take the carbon atom radius and the chlorine atom radius, and that, when you add them together, that is called the bond length. Okay, so your book has some data on this. It's in one of the tables. I can't find it right now, but I know it's there somewhere. Darn, I can't find it, but I'm sure they have it somewhere, and they have it on OWL. But let me just tell you right here from my notes. The carbon, let's say this is a carbon and this is a chlorine. The carbon is 77 picometers, the radius, and the chlorine radius is 99 picometers. So you add them together, the bond length of a carbon chlorine is 176 picometers. So it's just, you add up the radii of the atoms involved to get the bond length that you are looking for. Okay, one thing I should tell you is that double bonds are shorter and stronger than single bonds, and triple bonds are also shorter and stronger than double bonds. So let me just give you some data here just so that I could impress you with it, and then we'll be all set. Here's a carbon-carbon bond, carbon-carbon double bond, carbon-carbon triple bond. So the length of this is 120 picometers. This one is 154 picometers. Notice how it got much smaller. And then the double bond is somewhere in the middle, 134 picometers. Okay, so as you have more multiple bonds, the bond length gets shorter and shorter. The bond energy, though, increases. So this is the strongest of all. It's 835 kilojoules per mole. That's the bond energy here. This one is 346 kilojoules per mole. Look at the difference there. And the double bond is 602 kilojoules per mole, at least from the data that I have here. These are all approximations, but they're good enough. Okay, we are completely done with chapter 9, guys, and the next set of videos will be chapter 10, where we are going to use all of the Lewis structures that we learned how to do in 9, and then we're going to draw them correctly and figure out the molecular shape and the electron geometry and the bond angles, and we'll figure out molecular polarity and all of that stuff. Okay, good. We're all set with 9.